Okay, let's start. Today's seminar will be about some remaining things. Okay, the first one, I think that we proved, we used Serre spectral sequence, and and something of homological type, something like this for Serre vibration with some coefficients. Oh, sorry. With coefficient in some ring R. And I said that we proved that if, for example, homologies of base and fiber are finitely generated, then homologies of E are finitely generated if R is Noetherian. If R is Noetherian, from this Noetherian implies that submodules and quotients, submodules of finitely generated are finitely generated. Quotients is always true, but for submodules it's true exactly for Noetherian rings. And we proved by spectral sequence that if homologies of B are finitely generated, for example, we proved that what we have done, that if homology of the total space are finitely generated, and for example of base, then homology of fiber. And if total and fiber, then base. We have done for the opposite direction. For the remaining third from two statement. If for fiber is true and for base is true. Why it's true for E? We also proved this, but we used that if these two modules are finitely generated, then these modules are finitely generated. Yes. It was not obvious, maybe. We used that. Did you remember this? Yes. We need that such modules finitely generated, and then it follows always that if we have spectral sequence, all diagonal elements are finitely generated, and then this element is finitely generated. It's true. But why these modules are finitely generated if this module is finitely generated? It's because, for example, it's because of Q-net spectral sequence. Because we know that, what is it? Maybe let me recall some Q-net spectral sequence particular case. What Q-net spectral sequence says that
maybe we can use formula Zeeman coefficient of state.
In general we cannot, because
but this is our case now. But this is just our case. I think we can say something from this.
Okay. In this situation we can, but we of course, yes. Yes. Let me recall. Q-net formula says that that if we have chain complexes such that Tor between them are 0, yes, positive, then we have spectral sequence something like this between homologies converges to homology of tensor product if and particular case is let L is chain complex which is concentrated in one dimension, in 0 dimension. Yes, it's just one module. Yes, in degree 0. Okay. Now then here it's L and G is 0, so this is Q, and spectral sequence has this form. Yes, and this is chain complex which is obtained by just a tensor product each degree k by this module L. Okay. Okay. And we have such spectral sequence, and even without of course, in such situation, we have that this is a homology of chain complex of free abelian group tensor with this module. Of course, because of this free abelian group over Z, we have the universal coefficient formula. But in general, we have that if these groups are these models are finitely generated, and this model is finitely generated, then these models are finitely generated, because if I have finitely generated module of a Noetherian ring, I have I have free resolution by finitely generated free modules. And then after tensor product with some finitely generated, I obtain chain complex of finitely generated model, and its homology is finitely generated. Okay. So of course this is finitely generated, and again, if we have stabilizing the convergent spectral sequence with finitely generated elements, the target is also finitely generated, because it has finite filtration with finitely generated quotients. Then it's finitely generated. Okay. So in general, it's finitely generated, and so we have that this thing is finitely generated. Yes, because it's homology of tensor product of the chain complex of these modules. So of course, yes, this is finitely generated. Over Noetherian ring, it's important that we used many times that submodels of finitely generated is finitely generated. This is not true in general, but for Noetherian rings, it's true. Okay. Well, for example, example of Noetherian ring is polynomial ring infinitely many variables over field. If you have infinitely many variables, it's not Noetherian, for example. Okay. So we have proved that from two of this, and for cohomology, we need to understand why this thing is finitely generated. Now this is QNet spectral sequence for X. It used something like this. No, in our particular case again. Or maybe yes. And we need understand why this thing is finitely generated if these models are finitely generated. So why is it true that X between finitely generated modules is finitely generated for finitely generated modules Mn? Now again, we can consider free resolution of finitely generated free modules of M, and then we use Hom to N and compute cohomologies. So we need to check that Hom from finitely generated to finitely generated is finitely generated, yes? That's what we need. No, in fact, we need only for free modules, maybe. No, okay, for free modules. But for free modules, no, yes, it's just, it's if it's finite, and it's finite sum, yes. Okay. But we also need spectral sequence for X, so please do this before exam, okay? Okay. No, now I want to, yes, some things about, for example, what consider again Serre spectral sequence. Serre spectral sequence. No, I don't know. Homological is not important. No, let's homological because it's multiplicative. Consider, for example, no, in general, let we have first quadrant spectral sequence, homological type, and consider, for example, this cell. It's E 0 Q second. All differentials have the following form. Yes? It's homological type spectral sequence, okay? So all inward differentials are zeros because it's first quadrant. So in fact, E infinity 0q is quotient of E second. So E second quotes to E2, okay? Oh, sorry, no, exactly opposite. It's kernel, yes? It's kernel of all differentials. Without quotients, it's exactly the kernel of all higher differentials. So it embeds to infinity. E infinity, it's kernel of all differential on E2. So E infinity embeds to, okay? Okay? Because it's zero of all differentials. It's kernel of all, it's intersection of kernel of all differentials. I have no inward differentials, but I have sometimes outward differentials, and I need to the third page goes only kernel of second differential. To the fourth page goes only kernel of third differential, and so on. Okay. So I have this inclusion. No, and this thing, I have my target HQ of E, and I have its homological type spectral sequence, so I have decreasing filtration on this target. And again, I have only this diagonal with only non-zero this quotient. So in fact, if it's decreasing filtration, it's FQ and F0, yes, F1 with quotient E0 Q infinity, so on. So in fact, this thing is a quotient of homology of total space, no, modulo something. So in fact I have quotient from homology of total space. Okay.
What can you repeat?
No, in general, H P plus Q has Hn has quotient. It's Fn, F0, F1 decreasing filtration, and Fp modulo Fp plus 1. It's E P n minus P infinity. No, and this is the first step.
Okay.
And what is it? This is by definition zero homology of B with this coefficient, so it's just a homology of fiber. And what is this map? No, it's map. It's used by inclusion of fiber on cohomology. I have inclusion of fiber, and this is exactly this map. No, if you wish, it's an exercise, but it's not very hard because it follows immediately from naturality of our spectral sequence. I can consider inclusion of point to my base, and if I have fibration, then I can restrict my fibration on this point, and I obtain fibration of this sort. And from considering this, and if so, I have map of two fibrations, so I have map of two fibrations. And if you consider this map of two fibrations, you obtain that this map is exactly induced by inclusion. Something like this. Okay. And no, it's an exercise if you want, but it follows from naturality and from this case. And opposite direction, if you consider this element, this cell, E2 P0, now I have no outward differentials, but I have some inward differentials. So it's quotient. It's P0 infinity. P0 infinity in its Chern is the final element of filtration. It's P filtration. It's exactly this element. So it embeds to HP of E. And this is now zero cohomology. We suppose that our fiber is connected, so it's cohomology of B. And this map is also induced by our fibration P on cohomologies. This also follows from naturality if you consider your fibration and then you consider consider this map P again. And that is, then the induced map, the induced fibration, it's identity with fiber point. And you have such map of fibrations. And from these two, from these two maps of vibration, you obtain maps of spectral sequences, and you obtain this so-called, it's sometimes called corner gomorphisms. Corner gomorphisms are just induced by inclusion of the fiber and projection of fibration itself. Okay, it's an exercise. It's an exercise that's for spectral sequence. If you consider this cell, then infinity embeds to it, infinity projects to from homology, and this composition is just induced by inclusion of fiber. And oppositely, from this to this, it's induced by projection itself. It follows from naturality and by considering these two, these vibrations, this inclusion vibration and this vibration. From these two cases and from naturality of spectral sequence of Serre, it's false. It's an exercise. Exercises. Particularly, we have that, for example, what if this gomorphism induced by fiber? What if this gomorphism is surjective? On homologies. If it's surjective, this means that, no, this is surjective. This is always surjective. But this means that this inclusion is surjective. Okay? It's equivalent to say this composition is surjective. If we believe that this composition is this composition, then this is always surjective. Then this means that this inclusion is surjective. This means that this inclusion is equality. Yes? So if it's surjective, then this is equality. But equality in this place means that this means that all differentials are zero on this cell, and because it's true for any, this means that all differentials are zero on this column. Okay. Mm-hmm. No, I say that let this composition is surjective. Okay.
No, this equality, I agree.
Yes, it's equality. But what does it mean, this equality? This is intersection of all kernels. If it's equality, then all kernels, it's a whole my group. So all differentials are zero, all higher differentials. If intersection of its kernel, it's my group itself. I have no restriction of my group.
Okay.
So all my differentials are zero. And in particular, for example, if I have that.
What do you mean when you say differentials from the column are zero?
No, the differentials from all elements of this column. Yes.
Yes, I understand. And on each.
Yes, if it's surjective in each dimension, yes. Then it's zero in each dimension. Mm-hmm.
Yes, on each dimension and on each list.
On the second list, for now. I say about no. Yes, of course. No, because it's zero on the second differential, then it lives on the third page, and so on. Yes, you're right. Yes, all differential on all pages on the first column. Yes, you're right. And now, but now, let we know, for example, that our spectral sequence, that we have something like this. That our spectral sequence have something like this. No, for example, it's finite CW complexes, and and for example, homology of one of them is free or something like this. So for simplicity, if we know something like this, then if I have that differentials are 0 on this thing, but also differentials are 0 on this thing, because this thing is just my lower row. So all differentials are also 0 by dimension reasons. But now by Leibniz formula, I obtain that all my differentials are zeros. Okay.
Once again.
No, my differential, my second differential, for example, on tensor product, I have Leibniz rule. And if I know that it's 0 on this thing it's always 0 because it's lower row. All differentials are 0 on lower row. So it's always x linear. So it's always something like this. And so if I know that this is 0 on my column, this column is HQF, this row is HPB. It's always 0. If I know that all differentials are 0 on homology of fiber, then it's always 0 on each tensor product of my elements. Okay?
Wait, so I have a question. Why is it always true? So I'll explain myself. So on the second page we have some differential, and then you say that.
Now I say about a second differential. Okay? Second differential is 0. Okay?
No, I understand. I don't understand why. So on the second page we had some arbitrary differential on our
Yes.
homology. And for this differential, so and then for example, if h
Yes.
of f is free.
Yes. Let me know this thing. Then our differential. No, our differential always.
So why the composition of this isomorphism? This is an isomorphism.
It's an isomorphism of algebras. It's multiplicative isomorphism.
Why is this isomorphism? So
It's an isomorphism of algebras. It's an isomorphism of algebras of rings. So, and I know that my differential satisfies Leibniz rule for this ring, so it's for this ring too. So this. No, it's x tensor 1 tensor y plus. Okay. So so my differential satisfies Leibniz rule for tensor product, yes, because it satisfies Leibniz rule for multiplication. Okay. And so if my differential is 0, so my differential is 0, and so on. So my second differential is 0, I obtain the third page is the same as the second page, and my third differential is 0 by the same reason, and so on. So all my differentials are 0. It says that my spectral sequence degenerates. It says that my spectral sequence degenerates. It means that all differentials are 0. So in fact, I obtain that infinity PQ it's HQ. And for example, if it's, no, I don't know, if for example it's free modules or something like this, then if I have such situation for free modules, then in our filtration in cohomology, if it's free, for example, free modules, no, or projective in general, I have filtration, decreasing filtration with these quotients. These quotients are free. If I have filtration with quotients are free, in fact, all my model is free because filtration. No, on the last step. No, in each step I have short Riemann sequence where this quotient is free. It's free, but if quotient is free, then I have a section, and in fact it's direct sum. So if all my quotients are free, all my extensions are trivial one. And so in fact, this is also free or projective module of this form. So we obtain that in this situation, cohomology of E is just as module. This is not this does not respect multiplication in general, because it was expressed about two filtrations on algebras with isomorphic quotient but not isomorphic algebras. It's not isomorphic as algebras, but as modules. It's just these extensions, not multiplicative, of course. They are trivial as extensions of modules. But as modules, we obtain that our homology of E is just tensor product of these modules. Of R, this is so-called Lerer-Hirsch theorem. Lerer-Hirsch theorem. It's something like this. That's as modules. We can formulate this also that in general you have that homology of total space is has module structure over B, no, you have this map, and this is ring map. And so if you have ring map between two rings, this ring is a module over this ring, and this R model isomorphism says in fact that this module is a free HB module if HF free. No, in fact, this is true. For this it's true. For R models, we need that it's also free. But in general, no, if we have that only this thing is free and this is surjective, then in fact from this we obtain that we can say that this is free sum of HP. But no, in general, this is true that if this is free and this is surjective on fibers, then this is free module. It's some reformulation. No, this is some not hard consequence of our arguments. Okay, and this is Liré-Hirsch theorem, something like this. From this theorem, you can construct Hersitic classes or something like this. Okay. No, we obtain that if it's 2 free, then this is just free R module. Okay, it's not very far from this statement. Okay. I need to do some clarifying comments about some things which was on the end of the previous lecture. First of all, you said let we now prove that we have Chern classes. You asked me last time. Let me prove this. It's very easy. Let we believe that we proved that the homology of BUN is a polynomial ring for some elements of even degrees. Let me prove this by Borel theorem. I need to do some comments about Borel theorem and Zeeman theorem, but this is true, but I need some comments about this. Okay, let's do that further. But now let me prove this. How we can? No, it's not exactly Chern classes maybe, but how we can construct Chern classes? As I said before, we consider embedding of maximal torus. Consider the induced map of classifying spaces, and on cohomology, I have embedding. No, I have map. I have map from my cohomology of BUN to cohomology of BTN. This is also polynomial ring, but it's important that this is all generators in degree 2. But here it's different degrees. Okay, and we need two things. The first one, it's why image of this map is in symmetric polynomials. It's what you asked before. It's because of the following argument. It's a topological argument. No, I want to check that image of cohomology of BUN in symmetric polynomial in cohomology BTN. What's symmetric polynomial? No, in fact, I have no symmetric. It's interchanging of some of my variables. Okay, it's some permutations of my variables. But permutation of these variables can be как это называется? Я даже по-русски забыл слово. Can be modeled by conjugation by some matrix, permutation matrix. Permutation of variables in my torus is conjugation by permutation matrix. No, it's matrix of it's permutation by basis vectors of my vector space. This matrix is from UN. No, permutation matrix are unitary. So so because of my unitary group is connected, path connected, I have a path from this permutation matrix with unit. So in fact, this map, this is map. If you wish, it's map from UN to UN, which induced permutation on my torus, for example. Okay, and this map is gamotopic to identity because this matrix is gamotopic to identity. So this permutation map is gamotopic to identity. Now, what does it mean? This means that if I consider BUN, this permutation map, BUN, BTN, permutation, BTN. I have this commutative diagram. This map is gamotopic to identity. So on homology, I obtain that. Oh, sorry. In opposite direction. On homology, I obtain homology BUN induced by permutation. Homology BTN. Here it's real permutation. And on homology. Here it's permutation of variables, but here it's identity because on this space, this map is a gamotopic to identity. On torus, this is not a gamotopic to identity, it's permutation of factors of torus. But on UN, permutation of variables is gamotopic to identity. So, no, and from this is exactly that image in symmetric polynomial because it's identical after permutation of variables, okay? Hmm? Okay? I have some map from UN to itself such that on torus it induced permutation of variables.
So it obtained that the image is symmetric.
No, if I have some element, it goes to its image and then to permutation. But at the same time, it goes to itself and to this image. So image and permutation of image is the same thing. So it's symmetric. Mm-hmm. Okay? Now here I use that permutation of variables on torus can be induced by some map on UN itself. And in UN, it's gamotopic to identity. So this means that on homology, my image is a symmetric polynomial. So I have this thing. Okay, now I know that my symmetric polynomials, it's Z of elementary symmetric polynomials. And I have this map. So this is exactly the same rings of the same degrees and so on. And only what I need to check that, in fact, this is splitting monomorphism. This is inclusion of direct summand as abelian groups. If it's true, then this is isomorphism, okay? If I check that this map is inclusion of direct summand also, then this will be implied that this map is isomorphism. Because I have of identity of ranks, for example. But it will be isomorphism of rings. And then these elements will be Chern classes. Okay, now I need to understand why this direct summand. And this again follows from spectral sequence, and we say this second before. It's the same argument. Now let's consider the following spectral sequence. What I need to check that if I have inclusion Tn to Un, then on cohomology, it's inclusion of direct summand. Now this is composition of some particular inclusions. I have Tn is U1 n. I have U1 n includes to U1 n minus 1 U2 to U1 n minus 2 U3 and so on. And so I need only check that, yes, it's true. Yes. Yes. So I need to check that U1 K U, I don't know, or maybe n minus K K to U1 n minus K minus 1 to K plus 1 induced inclusion of direct summand on cohomology. Something like this. Okay. Just 1 second. I think that it's something different, but no, more or less the same thing, but let me. No, okay, yes, no, it's true, but no, we know that. No, this is just torus. On cohomology, torus factor is just give you tensor product with some exterior algebra. So in fact, it enough to check that I can eliminate this torus from the left and from the right side. It's enough to check that this thing induced splitting homomorphism on cohomology, because after I add some additional torus factors, it does not the resulting map will also be including of direct summit, okay? Because we know what is it. We know what is it direct product with torus. It does not port it in direct summit. Okay? No, it's observation. So in fact, we need something like this. No, in fact, I can consider this at the same time. It's not very important here. But okay, let me consider something like this, for example. And here I need to consider another spectral sequence. For example, yes, because tensor homology of torus is free exterior algebra, free abelian groups. Yes. Of course, it's from unit formula. Now I can consider, if I have inclusion of two groups, I have the corresponding Serre spectral sequence, or Serre fibration. If I have two groups, inclusion of two groups, I have the following. I have GH. It's fiber bundle, but then I have classifying space, in fact, and this is fibration. No, you can also think this is fiber bundle. I have this fibration. This is topological fact, and now if I apply this fact to this observation, to this inclusion, I obtain that I have fibration with fiber UK plus 1 modulo U1 UK B U K B U1 yes B UK. What is it? No, maybe in a real case.
Sphere.
Oh no. No, this is sphere. Yeah, there's a sphere modular O1. O1 is Z2. It's antipodal map. Yeah. It's projective space. This is projective space. Yes. This is C, P, K. Because it's sphere modular U1. It's Hopf fibration. So I have, if I consider spectral sequence, I know that this is cohomology are free abelian groups in even degrees, because we know that it's a polynomial ring in even degrees. This is also free abelian groups in even degrees. First, this means that my spectral sequence degenerate. If you have spectral sequence, and this is something like this, this means that all this on the second page, this is not zero only if P and Q are even. Okay, it's not zero only if P and Q are even. Okay. But in this situation, all differentials are zero, because degree of my differential is R1 minus R, and one of these numbers are odd. So one of them change parity of one of the index. Okay. So if my all elements only in even cells, then my spectral sequence degenerate. And again, I have infinity page. Надо что-то сказать будет по этому поводу. Значит, my infinity page it's three groups. No, because I know that Homology of this is free. This is also free. It's free groups, free abelian groups. And I have finite filtration with free abelian quotients, and again, all extensions are trivial additively. And so additively, it's free abelian group. And moreover, сейчас, что я хотел доказать-то? Yes, and this inclusion, this is here, blah, blah, blah. Yes. I want to understand what is this, exactly this map on cohomology. But as I said before, this map on cohomology, it's map from this cell to no what? This inclusion cohomology, H, P, B, my subgroup, B, U, N, UK minus 1. It's my, okay, it's my total space, it's my E. It's my total space of my vibration. My total space have a surjection, yes? It has surjection. Surjection or, 1 second. No, it's, okay, let's begin with the base. My base is this space because it's E2, it's P02, because my spectral sequence degenerate, it's infinity, and it quotes. Oh no, it's final step. It's final step of my filtration. It embeds to my total space. And this composition by exercise, it's my P. This is P on cohomology. And as I said before, this is inclusion of direct summand, because I said before that all my extensions are additively trivial. Inclusion of all my filtrations are inclusion of direct summands of free abelian group to free abelian group is direct summand. Because it's quotient, of this, it's also free. It's free. It's P minus 1, 1 infinity. It's also free. So I have splittings here. So this is inclusion of direct summand. Okay? And this is what I want. That on cohomology, if I consider classifying spaces, then on cohomology it's inclusion of direct summand. It's what I wanted.
Could you repeat the last argument? Why is it?
No, as I said before, if I consider in general I have this quotient, and this composition it's induced map on cohomology by your vibration. In our situation, my spectral sequence degenerates, so I have equality here. And so my P on cohomology is just this inclusion of my last filtration. It's less filtration. On this thing I have some filtration, F0, F1, and Fp is exactly this one. It's the smallest filtration step. And I need to check that this inclusion in all my homology is direct summand. But if I have this inclusion, to the previous inclusion, to the previous filtration. It's quotient. It's P minus 1, 1 infinity, and this is a free abelian group because all these groups on my infinity page are infinity because my infinity page is the second page. All my groups are free abelian groups. Okay. In my spectral sequence, all these groups are free and they coincide with infinity, so it is all free. Because no, all my cohomology is cohomology of this thing with coefficients and cohomology of TPK. No, this is free abelian group, okay? So this free abelian group, so I have splitting. So this is free summand. And so on. Fp minus 1 to Fp minus 2, it's quotient if P minus 2, 1. It's also free, so it's also direct summand. And this is a composition of direct summands, okay? To the most one, to the HP itself. So all the summands are direct summands on cohomology. So this map is also direct summand. No, so I obtain characteristic Chern classes. I obtain that in cohomology is exactly a polynomial ring of symmetric polynomials. And you can do this for symplectic group also, and so on.
Could you say again why the spectral sequence degenerates into
Because in this spectral sequence I have no B is UK, BUK, and this is CPK. All these groups non-zero only if P and Q even. Okay. But my differential has this B degree, and one of them is change parity of one of your index. Yes. So if your spectral sequence concentrate only in even degrees, then it's degenerate by dimension reasons. Now after second page, of course you can maybe 0 and 1 page. It's maybe no, it can be it's general truth. It's degenerate from the first page where you can you have your spectral sequence. Okay. Now maybe I need to say something about Zeeman and Borel. Why, in fact, we have that the homology of BUK is polynomial ring? No, in fact, you also can use some induction and some spectral sequence of some vibration between BUN, because you have again the filtration of the same time. You have inclusion of subgroup, and quotient again is UN modulo UN minus 1. It's exactly sphere, so it's sphere vibration. So you can use some induction. But let me say something about Zeeman and Borel. I said something sometimes a little bit inaccurate the last time. I need do some correction. No, it's not important in general. I said the following Borel theorem. If we have spectral sequence, for example, okay, for our topological applications, it will be a homological type spectral sequence, maybe multiplicative also, yes, topological type spectral sequence, multiplicative spectral sequence of the following form. It's algebras. It converts to 0, to k, and all others are 0. And then I say what we want. For example, I want to say that if W, it's this vertical, it's target in its first quadrant, I have W here and V here. I want to say that if W is exterior algebra, on some generators, then V is polynomial algebra on generators of degree on 1 more, and vice versa. It's equivalent saying. Okay. How I prove this? I say something the following. Okay, consider I have exterior algebra. Consider these elements, and I say that I want to consider I have these elementary spectral sequences where I have one element x. It has only in dimension 2n minus 1. It has 2n dimensional differential only. Its image is y. And then in fact you have spectral sequence with 2n is L lambda x tensor k y, and after this it's zeros. It's k. Some elementary type. Yes, it's y. You have also x y. It goes to y squared and so on. Okay. It's 2n differential, and all other differentials are 0. It's some elementary spectral sequence. Yes. Okay. And you can consider such spectral sequence for these elements. You consider what if we denote the spectral sequence by E x y. You can consider the product of such spectral sequences and map to your spectral sequence. And by Zeeman theorem, it induced they both converged to 0, and it used isomorphism on vertical one. So by Zeeman theorem, it induced the isomorphism on horizontal one, but and vice versa. But how can I define image of y alpha? X alpha, it's my elements. But what's y alpha? I need that if I have element of my first column, of my 0 column, I need that it will be alive on the, if it's of degree 2n minus 1, it's odd degree because it's exterior algebra. But I need that it will be alive on 2n page. And only on 2n page I have some differential to the my 0 row. And then the image, it must be the image of this y alpha to define this map. In general, if you have first quadrant spectral sequence, if we consider some element of the 0 column, then it may be one differential is not 0 maybe. Then it's then this element is not alive on the next page. If the second differential 0, maybe the third differential is not 0. Then this element is not alive on the third page, and so on. And if it's on the kernel of all differentials, then it's alive on the infinite page. But the previous situation, if it's not on the kernel of all differentials, but if it's on kernels of all differentials except the last one, maybe I have some differential which is not 0, but on the last one. If it's on this 0 p, then it's p plus 1 differential. Then, no, such situation says that this element is transgressive. This element is transgressive. Transgressive element. Is such element such that alive for all differentials except the last one by dimension reasons. And this element on the 0 row also is transgressive if it's image of the if it's not image of all differentials except of the last one by dimension reasons. And so, in general, I need that all these generators of my serial algebra to be transgressive. If they do not alive on my page, then maybe I don't have image of 2n differential on this 2n minus 1 dimensional generator, and so I cannot define this element in my spectral sequence here. I cannot define image of my generator y here. Okay. To define that, in this spectral sequences, all these generators are transgressive by construction. So in image, they also must be transgressive. But maybe they're not transgressive in my spectral sequence. So in general, this argument only proves if I know that my exterior algebra generated by transgressive elements. Then it works. What if not? What if not? No, in fact, it's not very important. And now I have some comment about this. What if not? No, in general, it's almost also true. What if, it's also Borel theorem, is something like, in fact, the same thing, in fact. Why I cleared, because this is the same statement, in fact. If I have spectral sequence, multiplicative, homological type, and V is exterior algebra, and converges to 0, first quadrant. No, then, in fact, you can choose transgressive generators of your exterior algebra. You can choose transgressive generators of V. And then you can apply your Zeeman theorem and so on. And so you obtain that, in fact, transgressive. And so, in fact, then in W, sorry. Then V is polynomial. It's also of transgressive elements, and vice versa. If V is polynomial, you can choose transgressive elements, which is image of the maximal differential. And so by Zeeman theorem, it's. But why it's true? I am not sure that it's true in general, but it's true if you work over field. If it's algebras over field. If over field, then it's true. How it works? No, it's because at least of a field. But in fact, for topology, fields are enough. But for example, of a field, you can prove the following improving version of Zeeman theorem. What at the same assumptions. So we have two such spectral sequences as in Zeeman theorem. I have two spectral sequences, have maps, and this is of a field. It's some algebras of a field. The first quadrant, they converge to 0. No, in fact, Zeeman's is, if you consider our proof of Zeeman theorem, you will be obtained that in this proof it's not very important that they converge to 0. It's important that your map is isomorphic on infinity page. It's true if are zeros, but in general you only need that infinity page of your morphism is isomorphism. If it's true, then it always works. In our situation, it's much useful applications in topology when they converge to 0. Okay, then the homological type, multiplicative, multiplication is not important. Then if FPQ2 is standard product of one and another, P0 and 0Q. Then P0 isomorphism, if and only if 0Q isomorphism, it's our Zeeman theorem. But here I can in fact improve this by its Zeeman theorem, comparison theorem. I can improve it by the following addition. If it's isomorphism in degrees, then something like n, and monomorphism for n+1. This is equivalent to say that this thing is isomorphism for n-1 and inclusion for n. Why it's over field? Because because you need something like, maybe you need in proof something. In proof what I know, you need something like for two maps. If they are monomorphisms, then the tensor product is monomorphism. It's not true in general of an arbitrary ring, but it's true of a field. Here, because we say something about monomorphism, we need something about monomorphism, and maybe we need something like this. If it's mono, then it's mono. This is true of a field. So of a field, it's always true, and we, by not very hard modification of the proof, also by some induction, bunch of inductions, we can check this thing. It's some improved version of Zeeman theorem, of a field. Okay, if you wish it's exercise, it's not necessary exercise, but it's not very far from our proof of Zeeman theorem. It's also by inductions, very direct induction proof from spectral sequence itself. For example, you can consider proof in book Mimuratoda. It's something like homology or topology of Lie groups or something like this. In the last chapter about spectral sequence of Serre, you have this version of Zeeman theorem. Okay, topology of Lie groups or something like this. You have two books, and in the last chapter of the second book, you have this theorem. Okay, but now, if you have such improved version, how to prove this theorem of Borel? Something like this. Let I have such spectral sequence. Let we check. Proof by induction. So let we assume that I can choose transgressive generators in dimensions less than something. So let we have transgressive elements. Let we choose transgressive generators in degrees less than some n. And so we can assume that n is odd, because all generators are odd in my Serre algebra. it's transgressive. So I need to obtain transgressive generators in dimension n+2. Okay. No, in fact, I want to prove Borel's theorem of this form. I want to obtain the following theorem, that if I have a spectral sequence of this form converge to 0, then W is exterior algebra if and only if V is polynomial algebra.
Yes, but we did this. No?
Yes, but here it's comments why our previous proof is not it's almost correct, but not exactly correct. This is some corrections. Because it follows from Zeeman theorem, but to apply Zeeman theorems, I need that these generators are transgressive. And now I need to, I try to obtain transgressive generators. The general fact that for any element, for any such situation, in any such situation, I can choose transgressive generators, but if we over a field. Okay? So this is true of a field in general. This is true in general for transgressive over any ring, but for any exterior algebra it's over a field. Over a field. And now I want to prove that. I formulated the improved version of Zeeman theorem over fields, and now I can I want to prove this theorem by this improved Zeeman theorem for fields. Так. Okay, so we have by Zeeman theorem, I have transgressive elements, so I have my spectral sequences by dimension n-2 of this my spectral sequences. I have map to my spectral sequence, and by improved Zeeman theorem, I obtain that I have what here n-2. I have that V. I have that the map from polynomial algebra to my V is isomorphism in dimension n. I have that my inclusion of my elements transgressive to my W. It's isomorphism in dimension n-1, yes? Because no, it's isomorphism n-2, but all my generators are odd, and all my in all my degrees only odd. All even degrees are 0 and 0. So in fact, it's isomorphism for n-1 also, and injective. Stop. No, maybe it's isomorphism for n-2, and for n-1 it's injective because it's 0 here. Yes, it's 0 goes to something. It's injective. It's enough. So by Zeeman theorem, in fact, I have that this map for V, it's isomorphism for n-1. It's even, and injection for n. Yes. But what here? But n is odd. So in fact, for odd n, сейчас, one second, что я тут хочу сказать? Maybe. Нет, вот, okay, yes, it's okay. Yes, and injection n. N is odd. Okay. Now, n is odd very well. Maybe. Сейчас. Okay. Okay. Now I can. In n degree is 0 degree. Okay. Maybe. Сейчас. Что-то тут мне не нравится. N is odd, n-1. But here, yes, I have this improvement here. No, because I know that this is some subset of generators of my algebra, yes, of odd generators. So I have isomorphism n minus 2 in n minus 1, because I know that, yes, sorry, because I know that this algebra is external algebra also in odd dimensional degrees, in the same degrees. And I know that I choose generators for these degrees, So it's isomorphism. On the following degrees, it's even. It's all they're both 0. So it's isomorphism on n minus 1. And on n, it's injection because it's not 0, but it's injection because it's subalgebra generated by some generators on the external algebra. So it's injection of a field. So in fact, it's injection in n. Okay. Maybe it's not injection because maybe I have some additional generators in this degree. I don't know. But it's, of course, it's injection, okay? Okay. So yes, so from this, I obtain that it's isomorphism in n and injection in n plus 1. Yes, it's important from Zeeman theorem. And now, yes, but here n is odd. So in fact, if I have n plus 1, no, it's 0 here. It's inclusion of 0. I have inclusion of 0, n plus 1, yes. No, yes. And now, no, I consider, no, yes, and here I have inclusion of some vector spaces in degree n plus 1. It's even degree. So I have inclusion of my generators in to n plus 1 degree, inclusion of v n plus 1 to n plus 1. And I can add some basis elements. No, I can choose some base of complement, okay? Because it's vector space of a field. I have inclusion. So I can choose some basis of these elements. Y, oh yes, it's beta, it's beta. It's always beta. Because alpha I don't know. It's what I need. It's what I have. It's beta. No, yeah, it's statement. Yes, beta. And I can choose some basis of this complement. Basis of complement. Some elements. No, I can add this generator. Just add this generators in this degree. No, and it's all because now. Yes. Of course, I need that they must be transgressive. No, yes, okay, yes. It's from if we know that our spectral sequence has this form, it's multiplicative, and we already know generators of W. Then, in fact, if we have these elements in this new degree, n plus 1, no, they must die in infinity page because infinity page is 0. So it must be differential of something, but it cannot be differential of the not the last differential because all these elements are x and y of something, and we know that the differential is not of this form, in fact. No, because no, it's sometimes it's kind of no, if it's x and y something, no, y goes to 0 and it's x goes to some previous generator. So this differential is no, it's not new generator. It's indecomposable elements of it's in this part. Even if no, this part is exactly some elements of degree n plus 1, which is decomposable as products of some previous generators. And in fact, all lower differentials has images in this part. So new generators cannot be of this form. They cannot be image of differential of some elements of such form. They must be differentials of some new elements here, which wasn't here before. What? So this transgressive element. It's by induction. It's because we know that all my spectral sequence has this form. So if it's element here, it's some element from WV, And differential, in fact, has image in this element. Okay? Is it clear? Yes. These new elements, they are automatically transgressive because they knew, because more or less by construction. Because all previous differentials has image. No, if in this row they has image in this decomposable elements. In fact, by construction. So these new elements by construction they automatically transgressive. I obtain these new elements. No, and so on. And so I obtain that if I add this new basis, I obtain that this is alpha, it's isomorphism in degree n plus 1. And again, monomorphism n plus 2 because n plus 2 is odd, and so the next odd dimension is 0, 0 to something. It's injection. So by Zeeman theorem in the to the opposite direction, I obtain that these elements are transgressive. I have some elements here, and by Zeeman theorem, I can consider this my x alpha, y alpha to my spectral sequence in degrees to n, and obtain that this x alpha is isomorphism to degree n to my n to new generators. And this is what I want. So I construct this new generator for. Okay? Questions? I will ask you on the exam this. So please ask me questions. Ну окей. Ну в общем вот. So over field, if you have improved version of Zeeman theorem, then in fact you can correct this argument, and this argument works by induction. By this Zeeman theorem, you obtain this also Borel theorem, that if you have some generators over field, then over field you can consider transgressive generators, in fact, by this induction. And so obtain that this is equivalent statements. But it's over field. No, okay, but now, and also another clarifying comments and correction. But no, it's not correction. It's, we understood this previous time, but without recording. It's what is free algebra. How we prove that? Okay, no. Now in general it's enough, because in general we only know that if G is Lie group, then cohomology of G in any field coefficient is some Hopf algebra. It has multiplication cup product, and co-multiplication goes from multiplication in G. So it's Hopf algebra over field Hopf algebra. It's general algebraic theorem. No, it's also I think it's Borel theorem that Borel classified Hopf algebras over perfect fields, so-called perfect fields. No, for example, over Q, or field of zero characteristics. Any Hopf algebra as algebra is tensor product of polynomial algebras and extra-real algebras with some co-multiplication as algebras. But because if G is Lie group, it's finite dimensional, so it's finite dimensional, and all polynomial algebras are infinite dimensional. So because it's finite dimensional, it's some extra-real algebra of some elements of odd degrees. And so by these arguments we can suppose that, and yes, and of course, and we have spectral sequence. You have spectral sequence to be G with fiber G. It's contractible, so I have spectral sequence, Serre spectral sequence which converge to 0. And so by Borel theorem, again, I can choose transgressive generators, and I obtain that cohomology of BG with Q is polynomial. It's always true. We obtain that it's true. Okay, it's enough for us. For field, okay. But what about UN? For UN, we proved that. How we prove that cohomology of UN is extra-real algebra over Z? Again, for UN, for example, no, we used induction. We used this vibration, and by induction we obtained, but that additively, E infinity page is this algebra by induction, and because of this is free things. So as abelian group, this again all extensions are trivial additively because all groups are free abelian groups. So additively I have this thing, and now we wanted to check that this is also multiplicative true. And I said that if you have spectral sequence multiplicative such that it converges to something, and it converges to something free with some generators, then in fact target, if I have algebra, graded fielded algebra such that graded quotients are these things, then in fact this graded algebra is also free, no, of some things. And when we prove this, it's this proposition. No, we only need that what is free. What I mean when I say free? When I say free, I mean free graded commutative algebra. Because when we prove this, I need the following. I need some gamomorphism from PQ infinity from this algebra to H. I choose some images of generators. It's some lifting of generators on filtration. And then I say that, okay, if I have choose of generators, then I have algebra gomorphism from infinity. This is by definition freeness, yes, because freeness is why free object is free is when you have some generators and map from your object is the same thing as set of as the maps of generators, okay? But then what is free in fact? No, this means that the generators are homogeneous. So I have homogeneous element. If it's even degree, then it must be polynomial. Okay, it's okay. But if it's odd dimensional, no, I have that. If it's odd dimensional, no, it's not always true. Yes, it's not always zero. I only know that 2 is 0. So yes. So in general, if for example you have characteristic 2, then it's also polynomial. It's also polynomial generator. Odd degree, even degree is not important. If a characteristic is not 2, but maybe it's two torsion. What I want to say that if in your algebra you have no two torsion, then in fact, if you have odd degree, then it must be squared 0, and then it must generate extra factor. This is our situation in research because in our situation it's free abelian group, and this is also free abelian group. As abelian group, it's all extensions are trivial, and this as abelian group they are isomorphic. So it's free abelian group. It has no two torsion, and so if I consider odd dimensional generator of my free algebra, I have choose some image, then it's squared, it's 0 in my exterior algebra, and this squared is also 0 in my algebra because it has no two torsion, okay? In my target algebra. I don't know this homological algebra, but it has no torsion. Because it has no two torsion, any square of odd dimensional element is 0, okay? So, in fact, here, no, yes, my exterior algebra over odd dimensional elements really free for this algebra. They are free, such things are free for algebras without two torsion. Okay, in the sense that to define map from this algebra, I need to only define images of generators. It's not true for algebras with torsion because, for example, if I consider exterior algebra on one-dimensional generator and then consider f over f2 and f2x, просто polynomial. No, I can consider this map, but x1 to x1, but it cannot be extended to map of algebras. This not there is no, but this is graded commutative because over characteristic 2, graded commutative is just commutative. It's not the so square of odd dimensional degree it cannot be not 0. So this is not free. This is free over characteristic. But if you have no torsion, two torsion, then this is free algebra. So if you have no two torsion, free is exterior product of odd dimensional and polynomial on even dimensional, and it's okay. If you have two torsion, you have some exceptions. For example, if you in characteristic 2, then it's just polynomial in each degrees. No, okay, in our, so for example, this is true if our ring R, over which we consider this is free R modules, this is also free R modules. If your ring R has no two torsion, this all true, this all works. In sense that it's external algebras on odd degrees and polynomial algebra on even degrees. So if you have no two torsion in your ring, it works. It's also what's common. No, of course it's work for Z, and so this works for UN, and so we obtain, oh my god. So we obtain that homology of BUN. Yes, sorry, we obtain that homology of UN is external algebra multiplicatively. From this, from Q-net formula, you obtain again that for any field, it's external algebra of this field. Now, by Borel theorem over fields, you obtain that for any field, by Borel theorem and Zeeman theorem, you obtain that for any field, homology of BUN, it's a polynomial algebra of this field. So we obtain from this that for any field, it's polynomial algebra of these elements. No, and again, from this and from Q-net formula follows that as abelian groups, it's free abelian group in each degree, and this is just integer polynomial, integer algebra tensor K. And now it's also easy exercise. It's easy exercise that if you have graded algebra such that if you tensor it by any field, it will be polynomial algebra, then in fact it's polynomial algebra itself, over Z. So we obtain that it is in fact polynomial algebra. Now it's how we can correct our previous argument, because it works over field, but it's in fact it's not very hard. But of course you can choose this by induction directly, considering the same vibration, but only this vibration. If you consider this vibration, you always can do this directly. No, you cannot do this. Okay? This is exercise that if you have graded ring such that R tensor K is polynomial algebra of the fixed number of generators in fixed dimensions, then in fact for any field, then R is polynomial algebra. No, maybe n1 and K. So what? Okay, this was corrections and some remarks and some comments. Maybe now I wanted to say something about, yes. What if you have such spectral sequence, elementary one, but if you know that the opposite version, if you have VW, but you know that this is polynomial, if you know that vertical thing is polynomial, or you know that horizontal thing is exterior. No, then it works, but only for characteristic 0 fields. If characteristic 0 field is 0, then it works. Then it's V is polynomial, if and only if W is exterior. It's by the same arguments, but of Zeeman theorem. But no, by considering this elementary spectral sequence, if it's X, then it must be Y. Here it's XY. It kills XY. XY killed by Y squared goes to 2XY. But if your characteristic is 0, you can consider a squared a half, and now it goes to here and killed xy. Okay. No, I want to spectral sequence which converts to 0. I need to kill all my elements. Okay. By differentials, and so on. So I have polynomial algebra vertically, which kills my x polynomial algebra. And here I have lambda x, here I have polynomial algebra. And this elementary algebra, by Zeeman theorem, you obtain this thing. But no, we see that this works only over characteristic 0, because we have something like this. And in fact, no, from this you obtain, for example, that again, if you have okay, for example, consider sphere and consider loops on sphere. Yes, and this is another. No, we have two sources of spectral sequences which converge to 0. The first source is for groups. We have this vibration with contractible total space, and another source for any topological space. For any topological, it's fiber bundle. For any topological space, we have Serre path vibration. This thing, paths. You know what is it? It's path space which fixed start or end of interval. For example, with fixed start, it maps from interval to x with fixed start, fixed point. Okay? Path space with fixed start. And this map is in fact a vibration. It's Gurevich vibration and Serre vibration, which ascends gamma to the end. And its fibers, all fibers are gammotopically equivalent because it's vibration. So for example, so fiber over this point, it just loops. It's maps, it's paths with the same end and start. Yes, okay. So its fiber is loop space, and this map is contractible. This space is contractible. So we obtain a spectral sequence for homology and cohomology of this form. Converge to 0, no, to k, to r in 0, 0. For example, oh, hello. For example, if we consider X a sphere, then cohomology of sphere, the first row, the 0 row, is just if it's odd dimensional sphere, then it's extrareal algebra. X n minus 1 is extrareal algebra. And by this argument of a Q, for example, you obtain that rational homology of fiber of loops of a odd dimensional sphere. Now, of course, it's polynomial algebra. Y 2 n minus 2. But no, of course, it's not true over Z. For example, because you need to kill this element, so it must be some element y1 in dimension 2n minus 2. Then it's element y1x, so it must be something like here, some element y2, which kills here. Of course, I have 1, 1 squared, but 1, 1 squared goes to 2, 1, 1x, okay, by differential. Okay? As to y2. So the difference is a cycle. I don't need cycles here because it converges to 0. So in fact, this is 0. So in fact, I obtain this is 2, 1 squared, and so on. And in fact, if you continue this procedure, you obtain that in fact cohomology ring of loops is so-called divided powers. Cohomology of loops of odd dimensional sphere over Z. It's so-called divided powers. 1, 1, 2, No, it's algebra where no, it's dimension of yi is I to n minus 2, and multiplication is so-called, it's something like this, KL, it's yk plus L, and here is binomial coefficients. This is called divided powers algebra, and this is a homology of sphere. If you tensor it with Q, then you can change generators and obtain that this is polynomial algebra in one generator in this dimension. But over Z it's not polynomial algebra. It's the minimal algebra which kills extrareal algebra in this spectral sequence, okay? For even dimensional sphere, you have not divided power, you have divided power and one another extrareal algebra. No, you can do this if you want for odd dimensional. Because for odd dimensional, no, okay. Because for odd dimensional, this element is odd dimensional. Sorry, for even dimensional sphere, this is even dimensional element. So we have odd dimensional here, and so you haven't squared element. So, no, okay. So you need some another element here to kill this. Okay.